first, before we go to the next speaker, I just wanted to mention the poster there is on work related to noise and noise sensitivity, work started by Oded. So for those of you who are more interested in that, they might want to have a look. And now our next speaker is Lyons, who will give a whiteboard talk.
Thanks, Christian. So I'm told that I have 5 less minutes than is scheduled. Hopefully I'll end on time. I'm talking about hyperfinite graph limits, work of Oded. This is one of his last topics, although Omer this morning introduced what it was about, although he was mainly concerned with a particular case. And Oded's last solo paper was called Hyperfinite Graph Limits. And that's what I want to talk about. The notion of this convergence, discrete limits in graphs, is, I believe, due to Itai and Oded, although it was discovered independently by some others shortly afterwards. So let me just remind you briefly what it is. Here's just one example. We might have the square lattice as a limit graph. Now these graphs actually have to be rooted, although for this graph it doesn't matter which vertex you take as root. And this would be a limit of, for example, big square portions, finite graphs of the square lattice, where you take a uniformly chosen root and you look at the neighborhoods of that root, and you see that what you'll see is exactly the neighborhoods here, unless you're close to the boundary, but very few vertices are close to the boundary. You also get the same limit if you took square graphs on a torus, and finer and finer grids. Now, by contrast, if you take a regular tree and you take a big portion of that and take a uniform root, you will not get as a limit the rooted tree, because most vertices are near the boundary, opposite to this case, and things look very different there. On the other hand, if you take a random regular graph or expander graphs with large girth, and take a random root, you will get in the limit a rooted regular tree. Now the limit will not necessarily be a fixed graph. It can be a random graph with a root. Okay? And I'm going to give a general theorem of Oded's, but if you're not familiar with this concept, you probably just want to think about the case where you have a fixed graph. Now, and I'm also going to assume that all the degrees everywhere are bounded by some number m. Now, the question that Oded looked at in this paper is, when is the limit graph or limit measure concentrated on small graphs like this, as opposed to big graphs like the tree? In other words, amenable versus non-amenable. Now, it turns out that actually another word for amenable in this context is hyperfinite, which is decades old. Before I get into the definitions, let me just mention that the result, which is a fairly abstract result that Oded proved in this paper, although it's quite interesting, was actually used by him, Itai, and Asaf Shapira in a paper where they applied a slightly more quantitative version of the result to what's called property testing in computer science. I won't go into that, but it actually had a fairly concrete application. So it turns out that the key notion was invented by Gabor Elek about a sequence of graphs, or more generally a family, but for us a sequence will be enough. So he defined a family or sequence, and these are finite graphs, which we're thinking of as what we're interested in taking the limit of. So the family itself is called hyperfinite. So they're already finite. So what does it mean by hyperfinite? There's some sort of uniformity about how they're put together. You can break them up into finite pieces in a uniform way. So in other words, for all epsilon greater than 0, there exists a finite k. And now as the uniformly in n, the graph Gn is k epsilon hyperfinite. And what does that mean? there exists a set of edges, S, in Gn, such that if I delete those edges and take them away, then I'll get all components of size at most k, but I haven't deleted very much. So in other words, the number of edges, and actually we're normalizing by the number of vertices of Gn, is less than epsilon. So I'm not deleting very much. And all the connected components, which I'm calling clusters, of G minus S have at most k vertices. Okay? Now, it's not so clear. That's a somewhat complicated definition. What graphs are hyperfinite? Well, actually, one example that you can give is the family of planar graphs. Planar finite graphs are, the whole family is hyperfinite. There's a theorem in computer science called the planar separator theorem, which tells you this. And in fact, the property testing paper that I mentioned, the primary example is planarity, testing planarity. But they mention other properties as well. Yes? No. That's the uniformity. Okay? What?
Planar, what is it?
Well, it depends on epsilon. If for each epsilon is a smaller epsilon, you get a bigger k you're going to have to take. Now, right. So we're interested in taking limits of such things. Now, it's easy to see that if we take a limit of a hyperfinite sequence, if the limit exists, random weak limit exists, then the limiting measure or graph also inherits a similar property. In other words, remember, we're taking Gn in a uniform root. And S is sitting somewhere. There's a fixed S. I fixed epsilon, fixed k, and there's a fixed S that witnesses this, okay? Then I take a uniform root. I get a random rooted graph with this deleted or marked edge set S somewhere, right? And it breaks up my random rooted graph, which is the same graph Gn, into random pieces. Now, if I take a limit of this, what I see locally is how the limit is defined, right? Now, if Gn has a limit, that doesn't mean that Gn with S also has a limit, but I could take a subsequence that will still have a limit point, a limit. And then I'll see a random S inside my random rooted graph. It won't be very much of the graph, because what does this statement mean? This says if I take a random vertex, the chance that it's near S is small. Also, all the clusters have size at most k. That's certainly preserved in the limit. K is fixed. So what I'll get in the limit is also some random deletion of a small number of edges, small density of edges, leaving only components of size at most k. Now, so what Oded did is formalize that notion and prove that it has a characterization. Those are exactly the limits of hyperfinite sequences. In other words, any such thing is a limit of hyperfinite sequences. That's the converse. So let me say what the Oded's definition is. So I have a measure mu, a probability measure on rooted graphs. And the definition will be similar to like this. So what I need to define is k epsilon hyperfinite. And then it's called hyperfinite if for all epsilon there exists a k such that it's k epsilon hyperfinite. Now, even if mu is just a fixed graph with a fixed root, the S might not be fixed. I still will let S to be random. Yes?
I have a question. So what does the index n have to do with? You see there's an index.
In this definition here,
Yeah.
it's uniform in n.
Is it
That's all.
It's index.
Same epsilon and k work for
Oh,
all
I mean,
n.
the set could be just any countable set.
Well, S sits inside E of Gn.
So it's part
It
of
says for every n.
It's Sn. It's Sn.
Yes, any
Well, if you want, yeah. Sn if you want.
So that's what I'm saying, that, I mean, it's just
This is
some
GN
kind of
over
set
here.
of the sequence of the index doesn't matter. I don't see the index n show up. It doesn't say bird.
Well, it shows up now. Okay, so S might now be random. It doesn't have to be fixed. So that's going to mean a probability measure, which I'll call new. And it's going to be an adjective I need to put in, which I'll postpone for the moment. So the probability measure new. Now, mu was on rooted graphs, G, and I'll call O the root. So now I have S. So nu is on triples, G, O, and S. Well, the new law of GO is mu. That's what I'm starting with. S is a set of edges in G. So I'm just going in turn of the conditions. Now this next thing is really about how often S touches the root. So I look at the degree of the root in G with S deleted on average. Okay? That's less than 2 epsilon. There's a 2 because it can come from either endpoint. I won't go into the details, but it's really equivalent to that if you just took a random root there. And finally, the last thing, nu almost surely, all clusters of G minus S have at most k vertices. Okay, now there's enough space for an adjective here, and that is, if you remember from, I forget which talk it was, Ule's talk yesterday, the condition of unimodularity came up for percolation. Well, it turns out that unimodular is also defined in this context. Finite graphs are, in a sense, unimodular already, and that's preserved. Unimodular is a mass transport concept, and I don't think I have time to go into it. If I do, I'll say what it is at the end. And so my assumption will be that mu is unimodular, and nu also is required to be unimodular. Yes?
Are you sure that when in the integral you want the degree of O in G minus S?
As opposed to?
The degree in S. Degree in S or something?
S is what I'm deleting. Oh,
But you want that S is small.
you're right. Yes, thank you. Yeah, thanks. This graph is definitely unimodular. Katie graphs are unimodular. So if you're not familiar with the concept, it's just going to be automatically satisfied, and you don't have to worry about it. But it's always true that limits of finite graph sequences are unimodular. So if we want to characterize what we get as limits, we have to put in unimodular anyway. And so Oded's theorem is that, so first of all, it's easy that a limit of a hyperfinite graph sequence is hyperfinite with this definition. And Oded's theorem is the converse. Anytime you have any measure which satisfies this, that is, for all epsilon, there exists a k such that it's k epsilon hyperfinite, then, and you have a graph sequence which tends to it, then actually that graph sequence itself is already hyperfinite. You cannot get as a small limit, you cannot get a small limit by big graphs. So let me write down the theorem. In fact, somewhat quantitative version of it already appears in this paper, just with the k and epsilon.
Did you say hyperfinite is equivalent to mutable?
Oh yes, I wanted to say that. Thank you. Okay, so I haven't defined what I mean by mutable, but there are various ways to define it. you don't really need to be explicit about how big things are. One way to define it is there is a unimodular way of breaking it up into finite pieces, not with a bounded size, but taking away just a small amount. In the case where you have a fixed graph that's transitive, it just means there are big pieces with small boundary. So you can just think about it in that context. Okay?
It's equivalent to being amenable conditioned on it being...
There's a tricky, subtle point, and I don't want to get into about that. But it's not conditioned. No, it's different. Okay, if mu is k epsilon hyperfinite, and Gn has random weak limit mu, then for all large n, Gn is k epsilon tilde hyperfinite, where epsilon tilde is equal to 4m epsilon plus 6 times m plus 1 epsilon times log of 1 over epsilon. So how would you show that given any graph sequence with this limit, you can, and the fact that you can break up the limit in a nice way means that you can break up the sequences, the finite graphs, in a similar way. That's the issue. And so Oded had a very nice idea, is to show that, so the definition of being k epsilon hyperfinite means there's some witness, there's this measure nu. Well, that nu you may not be able to use on the Gn. He wants to find a different witness created from nu that you will be able to apply or emulate on the Gn. So what kind of measure, just think of a fixed graph, what kind of measure here would be good, so good that you could essentially apply it to finite graphs which look like it? Well, what does it mean for a finite graph to look like it? It means that it looks like it on big neighborhoods. This means that what you're doing here should really only depend on a big neighborhood. So it should be a local decision about what you remove. So what he's going to do is take the given nu and use it to create another one which is just local. And then he can do it. And that's, okay. So that's the first very nice idea, and then of course the second thing is how do you carry it out? That's not as hard, I think, as maybe the first idea. But anyway, and let me just mention before giving the idea that this is similar to what's used in the theory of random regular graphs. People often want to count various things in random regular graphs. They're asymptotics, and they sometimes want to create things to provide lower bounds, the existence of certain things. And the way they very, very often do it is by taking, starting with IID numbers on all the vertices, say, and using that locally to decide what to do after a few steps. In fact, you can also do that on the tree, a regular tree, and start with those same labels and do the same kind of thing. And essentially, although they even mention that sometimes. So essentially, it's a similar idea where you're doing local information on a limit that you could also have done on the finite graphs. Okay, so let me give the proof. I need a little bit of notation. How much?
5 plus minus epsilon.
No. But we'll see how far we get. Okay, so K of O is the cluster of the root in G minus S. Now, here are some of the key definitions. So the probability that the cluster of the root is a given fixed finite graph K given the rooted graph GO. Or actually, we're just looking at vertex sets. So when I say the cluster, it's really just the vertices in the cluster. And we're only going to look at K of size of most, big K of size of most little k, because all the clusters are of size of most k. Now that's a little tricky to define in the general setting, but if you just think of G as a fixed graph, then that's perfectly fine. I just have some vertices, so those 4, and the chance that when I take away S, that's the cluster of the root. Okay? Now the problem, that of course, it depends on S. The randomness here is on S, right? And that is not local, or we're certainly not given that as local at all. So the idea is to transform this to a local thing. So that's going to depend on some radius r. P tilde sub r of Kn. So we're going to have some large r, and all the things that within distance r of my given k. That's probably not exactly accurate, but anyway, we're given a k and an n, and we're not given what the graph is outside, although for a fixed graph it doesn't vary. But we're not given what S is outside n either, only what's inside n. Okay? And so r is going to be, so it's the r neighborhood of k. Now as r tends to infinity, what happens? We're getting more and more information. We're getting all this information in the end, and so this converges. Almost surely. And that's what we're going to use for approximation. We'll take an r large enough, depending on the epsilon we're given in the beginning, to make that close. So I think I'll have time at least to give the definitions of how it works, even though I won't be able to give the proof that it works. So then it'll be an exercise to work it out. Okay, so for a big K of size of most little k, I'm going to delete, or I'm going to choose these sets at random, or deleting their boundaries at random. So I'm going to let x sub k be a Bernoulli random variable. That means it takes values 0 and 1. They're going to be independent of each other, given GO, if in fact we have a random rooted graph. And the probability that it's 1 given GO will be, well, I'm going to stop writing the R. R is going to be, well, we're going to have to choose R later, but I'm not going to write it. So really, what we want is the probability of P tilde of K. So n is determined by k, so I'm not going to write it. Times log of 1 over epsilon. Well, that might be bigger than 1, and so we'll have to take the minimum with 1. And there's a multiplication by 2 just for convenience. Okay, so that's the definition. And now what are the, what's the new S? So every time xk turned out to be 1, consider all the edges in the boundary of such a k. That's the edge boundary, d sub b of k, all the edges that go from k to the outside of k. Those are going to be in our new set that we're going to remove. And that's good because whenever we remove edges here, what's inside is size of most k. But of course, we have to worry about what happens elsewhere, and we're just going to take everything else. Oh, well, okay. I need another notation first of all. These are the insides, W. And then all the other things, we're just going to remove everything that we need to make everything of size of most k. So all edges, F tilde is all edges incident to any vertex not in W. And then finally, S prime is F union F tilde. So that's the definition. So everything, so it's clear that when we remove S prime, all the components have size of most k. Because either they have size of most k because we removed the boundaries here, or if they weren't removed that way, we removed all the neighbors. So it has size of most 1. What we need to show, so what has to be shown is that the degree here is the most this 2 epsilon tilde. And well, you have to do some calculations. You know, these are independent, so a lot of the calculations are not hard. But yeah, it's not so hard after this. You have to be a little clever, but it's not so hard. But anyway, I'm out of time. So thanks for listening. Son?
So you mentioned property testing as an application course. Is there some other motivation?
Oh, Oded's original motivation, I believe, did not have anything to do with property testing. Gabrielic was visiting, and I think asked the question. Although Christian and Jennifer probably know a little bit more about how it arose.
Right, well, I think Gabor has a different version. He has a different formulation of the limit of this graph sequence, which involves some abstract sort of notion about non-standard logic or whatever, non-standard algebra. And in his version, it's just the other way around. The direction Oded had to prove is actually easy, and the other direction is hard. But it's obviously an interesting question, right? In which sense do these properties carry over to the infinite limit? Any more remarks, questions? Okay, so we have a 3-minute break.
To give a very quick, because people ask, so a little sort of sneak preview, so just to show that it exists. So there's lots of pictures, yeah, and you can give it to your children to read, and so it has lots of.
And is it on your webpage already?
It is gonna be. It's sort of, I'm in the last stage of revising it, so it has many. It has some sections on the circle packing, and I'm gonna put it on the archive in about a week or so. So you have to play Sokoban on the fly. Okay, so that's just that. Maybe I go to screen mode again. Well, there are so many topics that I thought about. I mean, I had to choose from, and it would have been a lot of fun to talk about. But so I should like to say that doing mathematics with Oded was like playing tennis with a champion, and I mean, not while you're not being a champion yourself. So there are these balls coming, and then you try to hit them back. But in the end, all the balls are in your court, and every once in a while you get one and you hit it back, but then it comes back at you full blast. And so there is actually a lot of unfinished projects that I'm now scrambling to try to finish. And so essentially, I picked the oldest one to talk about today, and that's the joint work with Kari and of course Oded. And well, there's another reason why I chose that topic, because it shows one aspect that I think did not come out so well here so far, but which was an important aspect of it, that's work, which is his computing skills. So he wasn't only a gifted mathematician, but he was also a very good programmer, and he loved playing with a computer, and that was an essential part. I mean, we all know the pictures that he drew, but maybe we don't know how much brain power went into these pictures. And so before starting doing that, I wanted to show one photo. I think everybody expects me to give some anecdotes, but I'm not sure if I really want to. I wanted to show at least this picture. This is Oded on the top of, anybody recognizes? Mike, maybe. It's a little Tahoma peak, and that was a climb that I think we both enjoyed. And Oded was such an unconventional person. He had such an amazing ability to question things. I mean, things that we totally take on faith and for granted, where we don't think twice. Yeah? And Oded would question and try a new approach. Yeah? And so what he did on that trip, we had to camp at a foot of a glacier, and Oded tried on that hike to not. I mean, it wasn't that he forgot. He didn't bring a sleeping bag. He said he wanted to try how it is. You know, he had that theory that, you know, if he just wraps himself in all the stuff that we brought, he's going to be warm enough. And everybody who worked with him probably knows he had these amazing numbers of ideas, and many of them did not quite work out. But, you know, if fractured, this was not a good idea. He was miserably cold that night. But still, we had a very good time. So now I'd like to do some math. And this is almost on the level. So first I want to give the motivation. But I think it needs a lot of motivation. So eventually we'll come to, some of you might not understand the motivation, and then don't worry. In the end, it's going to be very simple and almost like recreational math. But I should like to draw one picture if you wonder what is a quasicircle. So I give definitions that you might not understand. But a quasicircle is just a topological circle in the plane. And these objects, so basically the geometric definition is whenever you take 2 points, then the smaller arc, so they don't need to be rectifiable, so I don't want to talk about length, I just want to speak about diameter, but the smaller arc shouldn't go too far away. So the diameter of this arc here should not be much more than the distance of the endpoints. So what is not a quasicircle would be a thing like this, something that has a cusp. But then, so here you can take 2 points that are very nearby, but the curve sort of escapes. It has a large diameter as compared to the endpoints of the 2 points. And so those of you working with these random curves know that these random curves, they're not quasicircles, but they sort of are. They are like quasicircles with a small probability of seeing bad cusps. So some of Oded's insights, actually, what goes into his proof of Luby-Ray's random walk scaling limit being a simple curve, is somewhat motivated by at least the insights that he had from working with quasicircles. But, okay, so they appear as limit sets of quasi-Fuchsian groups. So I mean, in many ways. But so let's just give a definition here. So there is a conjecture of Cariastras. That's a celebrated paper on the area distortion. And so all that says, don't read it too carefully, but the Hausdorff dimension of a quasicircle, I just write it in this way. I want to take one of these quasicircles, and the Hausdorff dimension is should be at most 1 plus k squared. Somewhere we need to measure the roundishness, how bad these bottlenecks are. There's a parameter called k, and I'll explain in a second what it is. So that's a technical definition, and don't worry about it. If you don't know quasi-conformal maps, you'll not understand this. But there's a simpler way to express it, and that's the point that we all understand. It's about holomorphic motion. So an equivalent conjecture is this. Set the interval, -1, 1, and move each point holomorphically. So think of a point here, and we have a time parameter. But time is actually, now think of it as complex value, time in the unit disk. So we have a parameter that varies in the unit disk, and the motion of each point is an analytic function of time. And it should be a motion. So if I take 2 different points, they will not collide. They will never collide. So the definition of holomorphic motion is very simple. So we think of it as each point moves, that's the first coordinate. The second is the time coordinate. So we function from space, from time, into the plane. And the axioms are, so in the time parameter, it should be analytic function. Each point moves analytic. And the space parameter, it's injective. 2 points never collide. And of course, the motion starts at time 0 with a line segment. So we just move points. Okay, so then in that phrase, the conjecture is it's equivalent to saying whenever I have such a holomorphic motion, then at time k, what I see. So the motion of the interval at time k has Hausdorff dimension at most 1 plus k squared. So we'll see in a second what relevant sets are. But so this project, the motivation comes from studying this conjecture, and we had some upper bounds, and then there were some improvements, and then other people found better. In the end of this line of results that I won't mention, there's Smirnov proved actually the sharp theorem, the upper bound. So Stas proved that actually whenever you move a line segment holomorphically, the Hausdorff dimension is never more 1 plus time squared. But that leaves then the question open, what is a lower bound? Is it really sharp? And to date, it's still, I think, the best known estimate is what we get. We don't get 1 plus k squared, but we get a 1 plus essentially 0.6 k squared. So we exhibit one holomorphic motion of a line segment that gives you dimension close to 1 plus k squared. So maybe I should first show a picture of a holomorphic motion. So this is the motivation. If you don't like it, you can forget everything, because you'll see the new problem is going to be totally independent recreational math or stuff. So when I talk about examples of holomorphic motions. Okay, so one example is actually coming from Julia sets of say quadratic polynomials. And so here is a little picture. And actually here I should like to say, as you can see, I'm not too experienced with this. Okay, so when Istvan Krause from Helsinki saw the announcement of this talk, he said I might be interested in this program that his student Alexei Verekangas wrote. And this program illustrates very nicely some holomorphic motion. And here is the program again. So the parameter is the red point, and you can move it. That's the time parameter. And the set is actually the Julia set of the polynomial. The red point is at the moment is a point 0 in the complex plane. When we move it around, it's some parameter c, and the white set is the Julia set of z squared plus c. So when I move this around, so this is what we get. So you see the Julia set, and as long as you stay inside that main cardioid, you know, it's a simple curve. And when you go out, then there's something funny happens, some parabolic implosion and stuff, and then you see different sets. So towards the boundary of the main cardioid, things go bad. But anyway, it's a theorem. Basically, it's a Magnier-Sullivan. That's where holomorphic motions were invented, that if you stay inside this cardioid, the things stay nice curves, and they move holomorphically. Okay, so another example is actually snowflakes, and that's what the talk is going to be about eventually. I mean, so a snowflake is, you think of a line segment and you replace it like this, and then each line segment gets replaced by a smaller scaled copy of it, and you proceed. The limit set of that is going to be the snowflake. But we want to make the snowflake depending holomorphically on one parameter p. And so that one parameter p, how does that come? I mean, how do we create it? So now I want to explain how to make a holomorphic motion out of a snowflake. And so I'll show an animation, then you'll see right away how it looks. But so here's how it goes at first. So start with a line segment, and instead of doing this picture of the snowflake right away, I break it down into two parts. So the first step is I replace the line segment by a triangle, and the tip is going to be the parameter. And then in the next step, I replace each of these two line segments by, again, the triangle like this. And then each of these 4 line segments now gets replaced by another triangle. So in each step, you double the number of edges. But it's probably best to just not worry too much about it, but you just look at this picture. So we have a simple way of generating the sort of one generation of the snowflake. And then if you just looked at each even one, you see the sort of the standard iteration. All right, so that is best encoded by 2 maps. So there are 2 contractions, F0 and F1. And so these are maps, linear maps of the plane that map the point -1, 1 to the points, -1p and 1p. So 2 contractions, and they generate a limit set. Okay, so here is, so the main thing I want to talk about is Oded's program that he called Jordan that analyzes the limit set. And for instance, if you put in Jordan minus, there's an L that you can't really see here. 0.2, 0.25. That gives the limit set of this dynamical system where the parameter p is 0.2 plus I times 0.25. And the program, of course, I mean, everybody can write a program like that. That's not the point. But it tells you more. So first, before I tell you what the program actually does, I want to argue that the snowflake is a holomorphic motion in the sense that I described. You start with a line segment, which is p equals 0, and then the snowflake actually moves holomorphically. And this we can see best if we look at a few generations. So that's the dotted one is the second approximation. This one is now the fourth one. And we look at these corner points, and they do not change under subsequent refinements. So once they are set, then the next step I just change things here, but these guys are definitely point on that snowflake. So then it's very easy to see. You have the only parameter is this tip here, this p of the very first triangle, and all these corners are actually polynomials in p, and polynomials are of course holomorphic, and the rest of the curve are just limit points of these corner points, so they're limits of polynomials, so they're analytic too. So we do get a set that is moving where each point moves analytically in p. But now the question is, of course, is it a holomorphic motion? And the answer is, well, if these points don't collide, if this thing doesn't self-intersect. So we should ask ourselves, the problem is, find the set of parameters where this limit set is a non-self-intersecting, a simple curve. And at this point, I guess everybody can join again. You know, some of you might have fallen asleep. This has nothing to do with probability. And that's like Oded and I also, we spoke sort of different languages, had different sort of interests. And I do remember the very first time when I met him, and so he came to a talk that I gave in San Diego in '91. And I asked him afterwards, so I knew that he wasn't exactly a complex analyst, and so I asked him if it made sense to him, and he said, yeah, he could understand everything. And he didn't say anything else, and so I asked him some more, you know, if he liked it, and he said, well, he doesn't find it particularly interesting. So he was very honest. He was very gentle, very nice. He wouldn't have said it by himself, but once pressed for a comment, you know, he was also honest. And here too, the original problem was maybe not the most interesting one, but this problem he actually liked. Yeah, so this one really interested him. And so then he started working on trying to understand that set. And so there is first, it's very easy to see. Maybe here at this point I should show a little computer animation, and you can see better what the set looks like. Okay, so let's go. This is not Oded's program. This is a Finnish program. So here, the disk is a set of interesting parameters. The red dot is p, and what you see here is an approximation to the limit set, to the curve. And so if we draw more, then we see this is a curve, and you see you have to go quite close to the boundary to see that it starts self-intersecting. But as long as this curve is not self-intersecting, it's we have a holomorphic motion. Okay, so
it is non-self-intersecting as long as they intersect, right?
No, that's not true. So that's exactly the point. So this is what I want to do now. When is it self-intersecting? For what parameters? So it's sort of easy to see that outside the disk it will be self-intersecting. You can see just by drawing pictures, by computing the Hausdorff dimension has to be at least 2. Well, there are many ways to see that the outside cannot give simple curves. But the computer-aided theorem says the disk of radius 0.91. So a large part of the set is actually where you have a simple curve. And this is exactly the set. Yeah, so the black set is the set of parameters for which the curve is non-self-intersecting. The gray set is the set of points where it's probably intersecting. Okay. So what the program actually does is, if you take a point, it returns, it tells you if the curve is simple, it says yes, it's a simple curve. So it gives a test that tells you have a simple curve. If you're outside, it only says it's probably not. So the test works one way. And I want to say a few words how the test works. And so it was a bit of a surprise that you actually do get such a large set of parameters for which you have a simple curve. There are other models of two generators, sort of semi-groups. I think it's called the Barnsley set, where you just ask yourself whether you get connected sets. So there is a big industry. So it's a very special special problem. But yeah, very good question. Maybe I should. How much time do I have?
You have left
9 or 10 minutes. Okay, so I do have enough time to. But maybe I skip forward to, and then I'll come back here. The answer to your question is that's the only probability that's going to appear here. Probably not. So, okay, let's go forward. So, the program actually was also able to, and I actually don't quite know how Oded did it, because the program has many virtues, but it doesn't really scan for islands. But he found this island here. But unfortunately, so the program is able to prove, given that you assume enough accuracy, the program is able to prove that, for instance, this point gives a simple curve. Okay? The program at present does not prove that a certain curve does not give a simple curve. But theoretically, it's easier to prove non-simple. So if you really wanted to, you could write a program that actually shows that this is an island. But this we haven't really, or that hasn't really done. And you see that it's quite fine. Maybe I'll show you the picture. I'll skip forward first. This is what the program claims to be a simple curve. Okay. And it doesn't look very simple. But then it's a limit of non-simple curves. And so if you look at a certain approximation to it, so now this should be sort of before the limit, the curve that is supposed to be simple. And at least the beginning looks good, but then it doesn't look so clear what this is going to be. But here you start seeing that there is at least a good chance that it is simple. So it goes like, I think it goes like this, and then it goes around like this. And you see at least that it's very delicate. This is like the pre-stochastic phase where you have, well, like in SLE4, where you don't quite know whether it's going to self-touch or not. But that's what it is. Okay, so let's go backwards a little bit. And so I guess what I want to say is one of Oded's strong traits was to such a question. I think it's not really theoretically possible. I mean, it's probably not easy to come up or impossible to come up with a formula. Even the question of connectedness, who knows? But he just sat down and started to work on a computer program. And before I come to that, maybe I should answer, or I should say quickly how this actually gives us this dimension estimate. But that's sort of very easy for the expert. I mean, as I said, so in the black set, in that Jordan set, every curve is a simple curve. So if I restrict my motion to that set, then I do have a holomorphic motion. And how do I restrict to it? Just by conformally mapping a disk to this one and changing time by that conformal map, call it phi. So if I conformally make that thing round, then I have a holomorphic motion of a disk. And then it's very easy to compute the Hausdorff dimension of that self-similar set. It's just a similarity dimension. And when you put it all together, and then out comes a lower bound for the Hausdorff dimension, and you just the in radius of that set gives you control over the conformal map, and then that's an exercise for an undergraduate complex analysis, essentially. Well, let's say a graduate. But so this is not very difficult. So the main part is really to find the radius, the in radius of that set. Okay. All right, maybe we should stare at this for a little longer, and then we could ask ourselves, how would we test if a curve is simple? And I don't know. I mean, when I was a student and saw the snowflake and tried to prove myself that just a symmetric snowflake is a simple curve, I think this is not trivial. I mean, it's easy. It's a simple exercise, but it took me a few minutes then to use the symmetry. But here we have non-symmetric situation. Here it's very different. So how can you possibly attack this problem? And here's a little lemma that Oded found. It's very, very easy. Actually, it looks a bit longish. I should say where this comes from. Oded worked quite a lot on this. I mean, that's now the mid-90s actually. But so he even wrote a documentation to that program. And so this is the documentation. At some point I'll put this program also on the web. I had Andre, a graduate student from Michigan, help me getting the program running again, because the C++, some standards have changed, or libraries were not supported. So there's a long documentation that explains how it works. And so I was working through this in order to write up Well, okay, so somewhere here, some of the little observations that he had are actually, I mean, all of them are sort of easy to prove once you know them, but you wonder how he actually got them. And so here's one of them. This one is easy to find. So this is the test, actually. How can we test if a given curve is simple? I mean, one of these self-similar curves. And so here I haven't drawn the full curve, but imagine, so you remember the process, it comes out of these self-similarities. So we should think we refine each of these sets, so then we see a copy of the curve here, 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 and here, these 4 sets. And I label them just 0, 1, 0, 0, 1, 1, 1, 0, just because I have compositions of these maps F0, F1. And so that, if I don't take the line segment, but the actual limit set, I want to call this one S01, and this one is S00, just these guys. And so the test only requires you to see if in these 2 pictures this part intersects with that one. If this one intersects with that one, of course it's not simple. So test if they're not intersecting. And test if this one does not intersect that one, and that one doesn't intersect that one. That gives you the 3 tests of that one generation. Okay. And here you have the same for the 3rd generation. Just test, okay, this part and that one is already dealt with. Just test that this one doesn't intersect this not that, and this not that. So 3 more tests. You have 6 tests, and test those. And then if you decide that they are not intersecting, then you're done. Right? Okay, that requires a little argument. And when I tried to work this out, I had a teeny little bit of a problem. And it's sort of easy. How would you prove that you have a curve with certain self-similarities and that this test works? And in the end of the day, that's a nice little exercise to do. But the solution, at least my way of seeing that, is to say that here at that tip, what you see here, if you take these 4 arcs, that this is actually similar to the whole set, which you sort of expect by self-similarity, but it's not so clear, because what you see here is sort of, this is sort of the right part of the curve, and this is the left part. So it's like when you chop up the curve in the middle, but you put the right to the left and the left to the right, that together they still give the old thing, and the scaling factors are different. So actually I would like to ask Oded how you saw that. I can just compute it very easily that this is true. You can draw pictures and verify it. You can just compute these points. Say again?
The number of tests was polynomially in there.
Okay, so how do you actually execute the test? But so using that similarity, it's very easy to see here that if the curve so you take any 2 points on the curve and you ask yourself, okay, so the best way is probably I haven't quite explained how the curve should be parametrized. So the tip, I make the curve at time 1/2. And this one is if I want to parametrize it by -1, 1, well, okay, so maybe let's answer your question first. The test depends, how many tests do I have to perform? I mean, here I would have to know the limit set, and this I don't know. I don't know the set at the beginning. It's a limiting object. But what I can do is I take, that's the next idea of Oded's. He calls it the super ball. So you take the super ball, a disk that is mapped by both similarities into itself. So you find the smallest disk that is mapped into itself by both similarities. Maybe I should just show the proof by picture. So then you apply all these maps, F00, F01, and so on, and so you get these disks. If you know that the corresponding disks are disjoint, then you are done, because the arcs are inside those disks, sort of by definition of the disk. And if the test fails on the first level, then you go again. You do a few more iterates and so on. And when the disks become very small, then at some point when you reach the threshold, accuracy threshold, then you stop and you don't know. But if the test terminates and if the disks are disjoint, then you know that you're fine. So that's why the test is only sort of one way, and the number of steps is sort of depending on how far you are from the boundary of that set. Okay, so I should come to the end here, but we already discussed that set is quite complicated. It looks quite interesting. It seems to have islands. The corresponding sets, at least in these islands, would be interesting to study, and I think that's all I wanted to say about that set. I asked myself also, I went back to, okay, so that was one project where Oded used a heavy sort of, I mean, so some nice ideas and some heavy programming to at least make some progress on some question. But he'd made so many pictures. Why not pictures of SLE? And so he actually once wrote to me, so there's that statement that he did attempt some mathematical pictures of SLE, but he didn't trust them, and they looked very unstable. And then I actually tried to do some using pictures using something related to the Löwner equation, and I explained that to Oded, and he was very gentle and nice. He said, "I hope so, that the pictures are nice." He said, "I'm excited to see the pictures. I don't want to ruin your optimism, but looking at the simulations, blah blah." And so he describes this experience that with a loop erased random walk, we don't know if there are loops before they could prove it, and so. I think later, actually, he did trust the pictures to some extent, so I think he was happy that he thought he has seen some honest SLE pictures. And finally, those who have actually worked with him probably know that, at least in the SLE world, he was extremely good also with Mathematica, and he just wrote these amazing notebooks where he did all sorts of computations very quickly. And then, of course, then you can check them by hand. But so here he describes something interesting. Here he said, okay, so he learned from so in SLE sometimes you have these PDEs, and then you need to find a solution, and at least you get sub-solution and so on. So first he used the computer a lot to find these solutions, but Mathematica often doesn't like to solve equations. But so then he says he learned from playing with it and seeing solutions that it's actually better to guess it. And the last sentence is interesting. He says after he saw a few of these, he said, I got bold, and instead of trying to coax Mathematica into solving, I decided I just guessed the solution up to 1 or 2 free parameters, and it so far always worked. So he was sort of excited that he was actually sort of beating the computer and was doing better by just guessing and verifying. So I guess this is all I want to say. I would just want to conclude by saying that when I first met Oded in San Diego in '91, he introduced himself as a circle packer. And I thought to myself, I knew a little bit of circle packing in the basic, I thought to myself, this guy is a little bit narrow. Of course, I didn't tell him. And that was certainly the biggest misjudgment of my life. And so looking at this picture, I think he showed us a direction in many ways, and I trusted him both in mathematics and also in other questions. So in mathematics, sometimes I did not check his computations, and most of the time I did, but once or twice I just trusted him. And also on this hike, actually, on the way back down, I just trusted him. I was wiped out, and the glaciers were, crevasses were open, snow bridges. He was leading, and I was just thinking, okay. And actually, it was good. He was paying attention. I went over one snow bridge, which then gave way, and I think Mike Friedman, I should thank him for teaching Oded so much about. Oded was very aware. He was in self-arrest, and everything was just fine. It was just me, just trusting Oded, and that was a great thing. He was a rock in my world in mathematics, and I miss him. Okay, thank you.